everybody. In response to some of the questions about drawing Lewis dot diagrams, I thought I'd make a quick video here to kind of illustrate some of the concepts. In one of the previous assignments, you have been drawing the Lewis dot diagrams of individual elements, and from those diagrams we are inferring the number of bonds that we can expect in our final diagram, as well as whether or not non-bonding pairs exist. In the case of sulfur being a group 6 element, it has 6 valence electrons, which we see demonstrated on the page. The 2 single electrons correspond to the 2 number of bonds we expect sulfur to make. These 2 pairs of electrons are called non-bonding pairs. We expect to see those in our final diagram as well. It's worth noting that the octet rule describes that each element in our diagrams must have 4 pairs of electrons around it. There are a number of exceptions to this rule, namely hydrogen. Hydrogen with only 1 electron and having that in the 1s energy level only has 1 pair. Only. So if we were to look at the diagram, the first thing we need to do to draw a diagram, such as question number 12 in the last assignment, is to step number 1, total up the number of electron pairs. There are 2 hydrogen atoms and 1 sulfur atom. Each hydrogen contributes 1 valence electron, each sulfur 6 valence electrons, for a total of 8, meaning that there are 4 electron pairs that should be present in our final diagram. No more, no less. Our next step would be, in the guess and test method, to connect each element to the central atom with a single bond, as we see demonstrated thusly. The central element in each diagram will be the element with the greatest bond capacity and typically the lowest electronegativity. Both of those pieces of information you know already. You can draw the Lewis structure to figure out the bond capacity or expected number of bonds, or use your periodic table to determine the electronegativity of each element. Step number 3 is to fill out the octet of the peripheral elements first and the central elements last. So recall that hydrogen can only have 1 pair of electrons, here symbolized by that line or sigma bond. Hydrogen's full. The remaining 2 electron pairs are on the sulfur. Notice how each hydrogen forms 1 bond. That jives with what we expect to see. Sulfur we expect to form 2 bonds and have 2 non-bonding pairs, which we also see. Our final step is to review our diagram and modify as needed. Carbon disulfide, in our first step, has 16 total valence electrons, or 8 pairs. Carbon is our central atom because it has the greatest bond capacity. In this case, carbon would have the electron dot structure of 4 valence electrons. We expect it to form exactly 4 bonds and have 0 non-bonding pairs. Some of you can already infer that a double bond will be necessary to satisfy the bond capacity of each element in this diagram, but for the moment, let's pretend that we don't know that's going to happen, and let's follow the steps as needed. This is where step number 4 comes in. Let's fill out the bond capacities of our remaining elements. Remember, we're somewhat mindlessly following these steps right now. We had 8 pairs. Here we have 1, 2, 3, 4, 5, 6, 7, 8 pairs. We've used up all the pairs, but our carbon has only 2 pairs around it. This violates the octet rule. So, when reviewing our diagram as needed, we need to identify that one of these non-bonding pairs on the peripheral atom needs to become a pi bond. Another one of these non-bonding pairs would also need to become a pi bond. By converting these non-bonding pairs into shared pairs, we create double bonds between the carbons and the sulfurs. Our sulfur has 1, 2, 3, 4 pairs around it. Our other sulfur has 1, 2, 3, 4 pairs around it. Our carbon has 1, 2, 3, 4 pairs around it. Please note that carbon has its 4 bonds. Sulfur has its 2 bonds and 2 non-bonding pairs, just as we would expect. For the next example, number 12, we have carbon tetrabromide. We have a carbon, and we have 4 bromine atoms. Each carbon contributes 4 electrons, and each of our 4 bromine contributes 7 electrons. So that's 28 plus 4, that's 32 electrons, or 16 electron pairs. There you go. Our carbon, we're going to connect to each of our peripheral elements. Remember, carbon has the greatest bond capacity between it and bromine. If we were to draw out bromine, a group 7 element, would have 7 valence electrons. 7, there we go. We expect it to form 1 bond and have 3 non-bonding pairs in its final diagram. Now we have 16 pairs. We've used 4 of them, so 12 pairs remain. Let's fill out the octets, first of the outer elements and then the inner elements. So each of our bromines has a full complement of electrons, a satisfied octet rule. Each of them has 3 non-bonding pairs and 1 shared pairs. 3 non-bonding pairs and 1 shared pair. Our carbon in the center has 4 shared pairs. This is exactly as we would predict. Tricky one. SO2 is an exception to the octet rule. Our central atom, sulfur, will need to violate the octet rule and allow for more than 4 pairs of electrons around it. Let's see what that looks like. We have a sulfur, and we have 2 oxygen. Each sulfur contributes 6 electrons, and each oxygen also contributes 6 electrons. So recall from our electron configuration topic and our shortcuts on the periodic table that these are easily inferred from our periodic table's group number. Both elements are in group 6A and have 6 valence electrons, bringing our grand total to 18 electrons, or 9 pairs. Now, oxygen, with its 6 valence electrons, we expect to have 2 bonds and 2 non-bonding pairs. Now something's going to have to give here. Oxygen and sulfur are both going to be fighting for these electrons. And there's a number that tells us who wins, and it's called the electronegativity. Oxygen with its electronegativity of 3.5, and sulfur with its electronegativity of, if I remember correctly, 2.8, means that oxygen gets to win. So oxygen is going to take its preferred state, leaving sulfur to figure something out on its own. So let's draw our base diagram here. And 9, we're out of electrons, and sulfur does not have a satisfied octet. Well, this leaves us with some interesting options. Number 1, we can convert this non-bonding pair into a shared pair. This can help satisfy the octet of oxygen and sulfur. Sulfur, here we are, now has 4 pairs of electrons around it. But you'll notice that there's something strange going on here. This oxygen has 3 non-bonding pairs and a shared pair. This sulfur has 1 non-bonding pair and 3 shared pairs. This does not meet with our expectation. We expect oxygen to form 2 bonds, and we expect sulfur to form 2 bonds and have 2 non-bonding pairs. The issue becomes that this oxygen appears to have 7 valence electrons around it. That's 1 more than it's supposed to have. This sulfur here appears to have, if we understand these shared pairs to have 1 electron originating from each element, appears to have 1, 2, 3, 4, 5 around it. Well, that's 1 less than it's supposed to have. Let's see if we can draw this diagram another way so that it fits with our expectations. Sulfur is our central atom. We're going to convert another non-bonding pair into a shared pair here. And in so doing, we're going to create the final diagram of SO2. Now, what makes this diagram the best diagram for SO2 is that it satisfies the predicted electron structure of an oxygen atom, which is to say it should have 2 non-bonding pairs and 2 bonds. If we look in this diagram, we have 2 non-bonding pairs and 2 bonds. Now, sulfur is kind of stuck in the lurch here. But if we look closely, if each one of these shared pairs had a valence electron that originated from sulfur, 1, 2, 3, 4, 5, 6, that satisfies its valence count. So what happened here is a non-bonding pair was split to satisfy the oxygen. Oxygen gets what it wants, and the element in the middle is stuck trying to figure it out. There you go.